Let's go ahead and jot down the definition of a nucleophile, remembering that they are electron rich. They're very rich in electron density, so they may have an unshared pair of electrons, or they may be negatively charged. In either case, they are seeking electron deficient species, that is, seeking nuclei, so to speak. And so we call those species that a nucleophile seeks, we call them electrophiles. So we can go ahead and write down what some of the most common of the nucleophilic atoms are, particularly in biochemical reaction. These are oxygen, nitrogen, sulfur, and carbon. And in fact, I like to remember this by recalling that good nucleophiles or common nucleophiles are cons: carbon, oxygen, nitrogen, and sulfur. We could also review this to a little more extent by thinking back to the periodic table and picking out the particularly good nucleophiles. And in fact, we can recall that nucleophilicity actually parallels basicity. Oh my gosh, that's sexy. So let's bring over a copy of the periodic table and remind ourselves how we pick out good bases and good nucleophiles by the same trends. So looking at the periodic table, what we can note is that nucleophilicity actually increases down and to the left on the periodic table. So a good example is looking at chloride. Like the chloride anion, it would have a negative charge and would make a good nucleophile, but bromide, a bromide anion would be a better nucleophile, and ever yet, iodide anion would even be better. But now if we compare chloride to sulfide, the sulfide anion is a better nucleophile than the chloride anion. So we can kind of use our knowledge of the periodic table to help enhance our knowledge of those nucleophiles that are considered to be the best nucleophiles, those that are seeking the electron deficient centers within whatever molecule they are attacking. So let's go ahead and write down actually the overarching, well, I've used the general mechanism of nucleophilic attack. We might think of a nucleophile, maybe this is a sulfide anion. I'm just going to draw it in the general form with a negative charge and say, okay, here's our nucleophile. It's going to seek these electron deficient centers, carbonyl carbon being a quintessential example of an electrophilic center. So in comes our nucleophile attacking the electrophilic carbon in that carbonyl and tracing the electron pair popping up onto oxygen as the nucleophile attacks. Now, in the next step after addition, this electron pair is going to pop on down and eject off the leaving group. So we'll see the leaving group being X in this case, and getting the heck out of Dodge in the phase of the reaction that we call elimination. So this is a general mechanism here. We might also just review. Remember how we said good nucleophiles are also strong bases, so nucleophilicity paralleling basicity. I just like saying it. So what we see then is that good nucleophiles are strong bases, whereas good leaving groups are weak bases. So when you ask the question of, okay, well, what's the difference between this X constituent and the nucleophile, is that the X constituent was a weak base, whereas the nucleophile was a stronger base. So this gives you an idea of the general mechanism of the nucleophilic attack.
Water can act like a nucleophile under certain circumstances, and particularly when its concentration is high. It's weakly nucleophilic. And I don't want you guys to get carried away in this definition or this, example that I'm showing of water working like a nucleophile. I don't want you to get caught up in the details of the example itself, but I simply wanted to show you a scenario in which water is the nucleophile. So we can kind of see on here that water is interacting with this molecule here, which some of you will probably right off recognize as being a dipeptide. It's two amino acids linked together. But if you don't recognize it as being that, that's no problem because we haven't covered those yet. But I just want to show you that in certain cases, a water molecule certainly can act as a nucleophile, attacking the electrophilic carbonyl carbon of this amide bond. If those terms don't sound familiar, online there's an organic chemistry review that I would encourage you to go find. It's very short, but all it does is remind you of your functional groups and terminology of bonds like that. So that's an amide bond, that's a carbonyl carbon of that amide bond. So if you don't recognize those, go back and grab that review so you can get an up and up on those. Cool. So in this case then, that leads to a hydrolysis that you see happening there and the breaking of that amide bond. And we end up with two separate amino acids where that nucleophilic attack has occurred. It's interesting to note, though not necessarily pertinent to this conversation, that this reaction is actually thermodynamically favorable. And you can see by that equilibrium that is so. But it's really kinetically slow. Takes a long time. And so this actually ends up being enzyme catalyzed. So just FYI, here's an example of when water acts as a reactant at the active site of an enzyme and actually plays a role in that reaction. Now, you might be thinking to yourself, well, if that's the case, how does a dipeptide ever get built in the cell? Or how does a polypeptide and therefore a protein ever really get built in the cell? Well, let's think about that for a minute. If we want the reverse reaction to occur in which that bond, that amide bond is formed, then what would be one thing that you would want in terms of the enzyme that catalyzes that reverse reaction? What would need to be excluded from its active site? Water. You got it. Because it's the presence of water that leads to the hydrolysis of that bond. So it's going to be really important that that enzyme excludes water from its active site so that a condensation can occur. And of course, our favorite molecule that we'll get back to a little later, ATP, is involved to provide some driving power for that reaction as well. So this is just an example of water acting as a nucleophile. Don't get caught up in the details of the reaction itself. Recognize, though, that water is acting as a nucleophile. Sweet.